Sorry for monopolizing discussion.
The next paper it will be by Dr. Lei, and it will be on mechanisms of butane isomerization over platinum sulfate of zirconia.
Most of the work that I'm going to talk today has just been covered by Dr. Hart and by the comment from Professor Sachtler. So I will quickly go through the slide. I will basically just focus on the detail of the research that I did in Professor Sachtler's lab. The topic today is focused on the sulfate zirconia catalyst. Before I start, I would like to first acknowledge the co-worker in this research. And in fact, most of the work was done by Dr. Haiyang Liu, who is also in the audience there, and by Dr. Valeria Diva. And I would like to especially to acknowledge Professor Sachtler. And as I still remember that when I just started as a postdoc in Professor Sachtler's lab, I gave a talk in the catalysis seminar, and that's related to my PhD work about water-gas shift catalyst. In the end, he asked me a question about the mechanism which is related to the format species. And at that time, I had no idea about what format species is, especially related to that catalyst. And I can only answer that I didn't observe that on my spectrum. But that was the time when I realized that I really know very little in this area, and I would like to acknowledge that I learned almost everything that I know in this area to Professor Sachtler, especially from the day-to-day discussion with him. And sometimes the discussion can be very tough for me. As I remember, when I first started, I was working on hydrogen and deuterium exchange on platinum metal. And many times during the discussion, Professor Sachtler can quickly suggest exchange mechanism, and then he can quickly derive the mathematical equation and then calculate the theoretical product distribution in just a matter of a few minutes before I can figure out how many hydrogen and how many deuterium atoms in his formula. Then I have to spend hours to understand his handwritten formula. Fortunately, that research, we finished that in less than a year. But I did verify one hypothesis from him. In that case, we have a statistical binomial distribution, which has been calculated earlier by him already. And the subject today can be traced back from in the spring of '94 when Professor Sachtler showed us this paper from Su et al. As you can see, this is related to the promoted iron manganese sulfate zirconia, and they show very high activity for the isomerization of normal butane. And after this, we have a short discussion with Professor Sachtler in just a few minutes, and we all agree that we want to pursue in this area, and we want to understand what kind of acid site is in this kind of catalyst. Most of them has been called quote-unquote super acid, and we really want to find out what kind of acid site is on this catalyst. And the other thing is we also want to understand the mechanism for the isomerization on this class of catalysts. And today I will focus on the mechanism part. Just to give you a quick overview of our motivation, and some of them have been covered by Dr. Hart, that the isomerization going through a protonated cyclopropane ring here, and the opening of the ring has 3 pathways. The first pathway will give you back the original molecule, and the second pathway will give you an inverted normal butane. Only in the third pathway, which will give you the iso4 molecule. But as you can find out that this will require the formation of a primary carbenium ion. And it has been estimated that the reaction 3 is about 10 to the 10 times slower than 2 or 1 here. And only liquid superacid is able to form the primary carbenium ion at low temperature. That's when we start to wondering how does the isomerization is going on this kind of catalyst. And as you just heard about, Professor Sachtler mentioned the bimolecular mechanism. Indeed, this is an alternative way for the isomerization, which will not require a primary carbenium ion. This is first formed a butene from the normal butane here, and then you can form a carbenium ion, and by the reaction of the butene with the carbenium ion, you can form a Ca intermediate. And it will isomerize to give you the most stable form here, and followed by beta Cgen at this position, give you 2 iso4 fragments. And the next thing is, how do we verify this this mechanism? And one day, Professor Sachtler walked into our lab and suggested to us that we can do isotopic exchange experiment. The moment I hear that, I know that I'll be in trouble again. But it turns out that this time, his idea is really simple and straightforward, which is using the double label normal butane here. And you just have to look into the mass spectrum to see if you have only the original 2 carbon-13 in the molecule after reaction, and that will give us indication of an intermolecular pathway. If we find more than the 2 carbon-13 in the product, we know that we must have an intermolecular pathway here. Let me just show you the mass spectrum of the non-labeled carbon-13, which has a parent mass at 58 here. And this is for isobutane, you can see they have very different fragmentation pattern here. And this is a reaction of the normal butane after 1 hour. You can see the patterns gradually changing into the isofragment pattern, which indicates the reaction is going on. With carbon-13 labeled normal butane, you can see the parent mass is at mass 60, which has 2 carbon-13 labeled on the end. And after reaction, you can clearly see that you have 3 carbon-13 in the C4 molecule. You can even see a significant amount of 4 carbon-13 in the molecule. And we continue to analyze the data. And to our surprise, we actually found out that on both the promoted catalyst and non-promoted catalyst, we find out the distribution, which is very nicely correlated to a binomial distribution here. We have equal amount of carbon-13 and carbon-12. And this is the simple binomial distribution, and this is a percentage. As you can find, they give us very good correlation. And this clearly indicated that all the isobutane is come from the bimolecular pathway. In addition to the bimolecular pathway, we also found out something interesting. And this is a before reaction with double label molecule. And you can see that this is the parent mass here with 2 carbon-13. Here is a fragment from the mass. When the mass knock out 1 carbon-13, we have only 1 carbon-13 for the C3 fragment. And after the reaction for 1 hour, you can see for this particular sample, there isn't a lot of reaction product going on from here. But you can clearly see this fragment from the C3 molecule here already have 2 carbon-13 on this C3 fragment. This again tells us that indeed there is intramolecular wave. The intramolecular wave will only lead us to the inversion of this lone butane that would not give us the isobutane. And all the isobutane is going through this CA intermediate and to give us 2 iso fragments. Since we all know that this catalyst is deactivated very fast, therefore we were wondering what the effect of hydrogen will do in the catalyst, and we realized that the hydrogen may remove the coal and increase the catalyst life. And we also understand that we might have olefin in our mechanism, and that will slow the rate for this isomerization. As I can only quickly show you the result, and let me spend a little bit of time here. We did the sulfate zirconia on the hydrogen with higher pressure, and we found out that this catalyst deactivates. And by increasing the hydrogen here, you can find out a negative order here by the hydrogen effect. And therefore, what we think is that olefin is intermediate, and Professor Sachtler has suggested us that if we can put a little butene in the feed, we'll be able to increase the reaction rate. And he suggests we did a double layer experiment in which we put the platinum as the dehydrogenation site before our catalyst. Then we did the experiment. To our surprise, we found out that it has a reverse effect. We actually have lower rate here. So sometimes we cannot understand why it's that until we realize that in our feed we do have butene as impurity. By doing so, you actually lower the butene impurity concentration to the level of equilibrium. Therefore, you get a lower rate here. That's the time we realized that we need to have platinum in situ with the sulfate zirconia here. And in this way, when the reaction consumes the butene, the platinum can in situ regenerate the butene. I will stop here just to give you some more time if you have any question or comment. Thank you for your attention.
It was he who had this idea that the butene was an impurity in the feed, and he showed so. I was just flabbergasted that the catalyst had a lower rate than higher one. But you gave the answer, you had realized.
Any questions?
Another question also related to the previous talk. If the acid side or super acid side is actually necessary for the biomolecule activity?
Can you repeat again the acid side?
I mean, the acid side or super acid side is really necessary for doing this biomolecule activity.
No, I would not say the superacid site, since we didn't, in another part of research, we really didn't find any superacid site in this kind of catalyst.
From the mechanism, it seems that no acid site involved in the mechanism.
Oh yes, to initiate a reaction, you have to have acid site. Either you have Lewis acid site or you have bronze acid site. You can have bronze acid site for the carbonium ion mechanism, or you can have Lewis acid site for the hydride extraction to initiate the reaction.
I just want to make a comment on this reaction. Paul Weiss in our laboratory in the 60s did this kind of experiment with mordanite. And he was so clever to do two things. He had this platinum and silica in a separate reactor prior to the actually isomerization, and by controlling the temperature of this pre-Platinum catalyst, he could dial in a certain concentration of butene, depending on the thermodynamic equilibration between butane and butene. And it was low temperature, the reaction was essentially quenched. As you raise the temperature to 200 degrees or 300 degrees, then the reaction was turned on. So that was a adjustable butene level in the feed by virtue of the temperature of the pre-Platinum catalyst.
Okay, well, thank you, Dr. Lei.